When we close our eyes and imagine the beginning of everything, we almost instinctively picture a flash of blinding light. We imagine a fire, sudden and violent, erupting from a single point to consume the darkness. It is a natural intuition. In our daily lives, every explosion, every sudden release of energy is accompanied by heat. A match striking, a log crackling in the hearth, the engine of a car roaring to life. They all radiate warmth. So, when we turn our minds to the origin of the universe, that moment we call the Big Bang, we assume it must have begun as a furnace. We assume that the very first moment of time was also the hottest. But the story of our cosmic dawn is far more subtle and far more mysterious than a simple firecracker going off in the dark. Before there was heat, there was a profound, stretching silence. Before there was the fiery plasma that would eventually become stars and galaxies, there was a period of cold so absolute that it defies human comprehension. This is the era that cosmologists call the epoch of cosmic inflation. It is the silent prologue to the hot Big Bang, a time when the universe was not a cauldron of boiling particles, but a void dominated by a strange, silent form of energy waiting to be released. To understand how the universe became so hot, we must first understand how it started so incredibly cold. We have to travel back to a fraction of a second before the heat arrived, to a time when space itself was the only thing moving. Imagine, if you can, a vacuum. Not just an empty room where the air has been removed, but a region of space stripped of every single atom, every photon of light, every wisp of dust. In our modern universe, even the deepest voids between the galaxies are not truly empty. They are traversed by stray rays of starlight and the faint, ghostly wash of background radiation. But in this primordial epoch, the emptiness was different. It was a textured nothingness, a stage that was being built faster than the actors could arrive. In the early 20th century, astronomers discovered that our universe is expanding. The galaxies are drifting apart, carried along by the stretching of space itself. If you run this film in reverse, everything moves closer together, eventually converging into a dense, hot singularity. This was the original picture of the Big Bang, an infinitely hot point that just expanded. However, as scientists looked closer at the night sky, they found puzzles that this simple picture could not explain. They found that the universe was too smooth, too uniform. The temperature of the cosmos in one direction is almost exactly the same as the temperature in the opposite direction, even though those two regions have never been close enough to touch or exchange heat. To solve this, physicists realized there must have been an earlier chapter, a brief, violent burst of expansion that smoothed everything out. This is inflation, and this is where our story of the heat begins, ironically, with a deep freeze. During inflation, space did not just expand, it doubled, and then doubled again, and then doubled again, all in a fraction of a second so brief that our best clocks could not measure it. It expanded faster than the speed of light. This does not break the laws of physics, for while objects within space cannot travel faster than light, space itself has no such speed limit. It can stretch at whatever rate the laws of nature dictate. And in this first fraction of a second, it stretched with a ferocity that is impossible to visualize. Imagine drawing two dots on a balloon to represent two particles. As you blow up the balloon, the dots move apart. Now, imagine that balloon expanding from the size of a marble to the size of the entire visible universe in less than a billionth of a trillionth of a second. Those two dots would be ripped away from each other so fast that they would never see each other again. They would be alone in their own private horizons. This is why the inflationary universe was cold. In thermodynamics, the study of heat and energy, we know that when a gas expands, it cools down. You can feel this if you use a spray can of compressed air. As the gas rushes out and expands, the can feels cold against your fingers. The energy of the particles is spread out over a larger and larger volume, and so the temperature drops. Now, apply that principle to the universe itself. If there were any particles present at the very beginning, any pre-existing heat or radiation, the sudden exponential growth of inflation would have diluted them to nothingness. The density of particles would have dropped to zero. The temperature would have plummeted towards absolute zero. The universe became a vast, lonely desert of stretching geometry. It was a supercooled vacuum. It was dark, it was empty, and it was expanding at a rate that would tear any structure apart before it could even form. So, if the universe was a frozen, empty void expanding into nothingness, where did the fire come from? How did we get from a cold, dark vacuum to the blinding brilliance of the hot Big Bang? The answer lies in the empty space itself. We tend to think of empty space as a mere container, a box in which things happen. But in quantum physics, space is never truly just a container. It is a medium. It is alive with fields and potential. Just as the air in a room carries the potential for sound waves, and the magnetic field around a magnet carries the potential to pull on iron, the vacuum of the early universe was filled with a field. Physicists call this the inflaton field. You can think of it like a reservoir of water held back by a massive dam. The water in the reservoir is calm. It is not moving. It is not hot. But it holds an immense amount of potential energy simply because of where it is, sitting high up, waiting for gravity to pull it down. As long as the dam holds, the valley below remains dry and quiet. In the early universe, the inflaton field was that water behind the dam. It permeated every inch of space. It was not made of particles. It was a smooth, continuous sheet of energy spread throughout the cosmos. And just like the water behind the dam, it held a staggering amount of potential energy. This energy was not in the form of heat, which is the movement of particles, but in the form of vacuum energy. It was the energy of the fabric of space itself. This vacuum energy is what drove the expansion. It acted like a kind of reverse gravity. Normal matter, like the Earth or the Sun, pulls things together. But this high-energy vacuum pushed things apart. It exerted a repulsive pressure that caused the fabric of the cosmos to swell outward uncontrollably. It is a difficult concept to grasp, that emptiness can weigh something that nothingness can push. Imagine lifting a heavy stone and holding it above your head. As you hold it there, your muscles tense. The stone is stationary. It has no speed, no heat, no kinetic energy. But it has potential. If you were to let go, that potential would instantly turn into motion. The inflaton field was like that stone, held high above the ground, filling the entire universe with a tension that wanted to be released. For that tiny fraction of a second, the universe held its breath. The field remained stuck in this high-energy state, causing space to balloon outward. And as space grew, the field did not dilute. This is the miracle of the inflationary mechanism. Usually, if you have a box of gas and you double the size of the box, the gas gets half as dense. But the inflaton field was a property of space itself. When you made more space, you made more field. The total amount of energy in the universe grew exponentially, but it remained locked away, hidden in the silence of the vacuum. It was a universe of latent power. There was no light to see, for photons did not yet exist. There were no atoms to touch, for protons and electrons had not yet been born. There was only the relentless, accelerating stretch of the dark, cold fabric of reality, fueled by this pervasive, ghostly field. We can try to picture this era as a landscape. In physics, we often use the metaphor of a ball rolling down a hill to describe how fields change. Imagine a vast, misty plateau high up in the mountains. The inflaton field is a ball resting on this plateau. Because it is high up, it has high potential energy. As long as the ball stays on the plateau, the universe continues to expand wildly. It continues to supercool. The temperature drops lower and lower as the horizon stretches further and further. But the ball cannot stay on the plateau forever. The laws of quantum mechanics are restless. Everything in nature seeks a lower energy state. The water wants to flow down the dam. The stone wants to fall to the ground. The ball wants to roll down the hill to the valley floor. This impending transition is the key to our question. The reason the universe became so hot is that it started with so much stored potential. The coldness of inflation was not a lack of energy. It was a hoarding of it. The universe was like a drawn bowstring, pulled back to its absolute limit, trembling with the tension of the force stored within it. The further it was pulled, the colder and emptier it seemed. But the more violence was being promised in the release. As the expansion continued, the isolation of any stray particles became absolute. If you had been an observer in that epoch, you would have seen nothing. The expansion was so rapid that light from any distant point would be swept away faster than it could reach you. You would be encased in an event horizon that was shrinking around you, closing you off from the rest of existence. It was a time of supreme loneliness, and yet this silence was necessary. It was this very expansion that prepared the canvas for the cosmos we know today. By stretching space so aggressively, inflation smoothed out any wrinkles or warps in the fabric of the universe. It made the cosmos flat and uniform. It erased the chaotic, messy conditions that might have existed before, wiping the slate clean. It created a pristine, blank page, frozen and vast, ready for the story of matter to be written upon it. We often wonder about the conditions required for life. We think of water, of sunlight, of carbon. But long before those complex requirements could be met, the universe needed to be uniform. It needed to be large. If the universe had started hot and messy without this period of cold expansion, it might have collapsed back on itself in moments, or it might have been so crumpled and distorted that stars could never form. The cold silence of inflation was the calm that allowed the universe to grow large enough to eventually house us. But a cold, empty universe is a dead universe. Potential energy is useless unless it can be converted into something else. The water behind the dam had to fall. The ball had to roll off the plateau. The bowstring had to be released. The mystery of the heat is the mystery of how this field, this ghost in the machine, decided to end its reign. How does a vacuum, which by definition contains nothing, suddenly transform into a soup of billions upon billions of degrees? How does the energy of expansion convert itself into the energy of motion, which is what heat truly is? This process is known to physicists as reheating, though the term is perhaps a bit of a misnomer. It implies that the universe was hot, then got cold, and then got hot again. While that is possible, it is more accurate to think of it as the first heating, the preheating of the cosmos. It was the moment the universe switched fuel sources. It stopped running on the cold, repulsive energy of the vacuum and started running on the hot, kinetic energy of particles. We are standing at the precipice of the greatest transfer of energy in the history of time. We are lingering in the final moments of the inflationary epoch. The universe is incredibly large, incredibly smooth, and incredibly cold. The inflaton field is still dominating the dynamics of space, pushing the galaxies to be apart before they can even exist. But the stability is faltering. The ball is inching toward the edge of the plateau. The physics of the field are beginning to shift. The quantum fluctuations, tiny jitters in the energy field, are starting to pile up. The smooth sheet of the vacuum is developing microscopic ripples. These ripples are the seeds of everything we see today. They are the blueprints of galaxies, imprinted on the frozen vacuum like fossils in ice. But for now, they are just ghosts, potential variations in a sea of sameness. There is a deep beauty in this stillness. It reminds us that everything active and vibrant has its roots in something quiet and potential. A seed lies dormant in the cold winter earth before it bursts into the green warmth of spring. A thundercloud gathers its charge in the heavy, humid silence before the lightning strikes. The universe, too, had its winter. It had its heavy silence. The temperature is near absolute zero. The density of matter is zero. The darkness is total. But the energy density, the sheer amount of power locked in the fabric of space, is unimaginably high. It is a paradox, a universe that is simultaneously empty and full. Empty of things, but full of possibility. As we prepare to witness the end of this era, we must let go of our human intuition that connects energy with heat. We must accept that for a brief, shining moment, at the start of time, energy was cold. It was a structural property of the universe, not a chaotic motion within it. But the dam is about to break. The inflaton field is losing its grip on the high ground. The tension is becoming unsustainable. The expansion is about to shudder and change gears. We are approaching the event horizon of the Big Bang proper. In the next chapter of this journey, we will watch as the ball rolls down the hill. We will see what happens when the energy that was used to stretch the universe is suddenly, violently, dumped into the vacuum. We will witness the birth of the first particles, the ignition of the first light, and the sudden, cataclysmic rise in temperature that gave us the hot universe we reside in today. The silence is ending. The void is about to speak. The first true event of the material cosmos is at hand. To understand the fire that eventually consumed the cosmos, we must look closely at the fuel that fed it. We have established that the universe began in a state of profound cold, a vacuum that was not truly empty, but was alive with hidden potential. But what exactly was this potential? What kind of machinery allows nothingness to weigh something? To answer this, we have to become comfortable with one of the most fundamental, yet invisible building blocks of our reality: the field. In our modern world, we are used to thinking of the universe as a collection of objects. We see stars, planets, trees, and people. We imagine these objects moving through the emptiness of space like actors moving across a stage. But according to the deeper laws of physics, the objects are not the fundamental reality. The stage itself is what matters. The universe is filled with invisible fields, fluid-like substances that permeate every single point in space and time. Think of the air in a quiet room. You cannot see it, but it is there. If you wave your hand, you feel the resistance. If you speak, the air carries the sound. The air is a field of molecules. Now, imagine a magnetic field. It is invisible, yet it has the power to pull a piece of iron across a table. It has strength, it has energy, it has a presence, even though it has no solid form. In the first moments of cosmic history, the universe was dominated by a singular, all-encompassing entity known as the inflaton field. This was not a magnetic field, nor was it a gravitational field. It was something unique to that specific moment in time, a scalar field that held a very specific and strange property. It did not dilute. This is the crucial concept that defies our everyday intuition. If you take a bottle of perfume and break it in a large auditorium, the scent will spread out. As the gas expands to fill the room, it becomes thinner. The density drops. The energy is dispersed. This is how normal matter and normal energy behave. If you stretch a cloud of gas, it gets wispy. If you stretch a beam of light, it gets dimmer. But the inflaton field broke this rule. It was a property of space itself. As the universe expanded, the field did not get thinner. It stayed constant. Imagine a magical ocean where, if you stretch the water surface to make it twice as wide, new water simply appeared to fill the gap, keeping the depth exactly the same. The more space you created, the more field there was. And because the field was made of energy, the more space you created, the more energy you created. This seems like a violation of the most sacred rule in science, the conservation of energy. We are taught that energy cannot be created or destroyed. But in the strange, flexible geometry of general relativity, the rules are more subtle. As space stretches, the inflaton field extracts energy from the gravitational potential of the universe itself. It is the ultimate free lunch. The universe was printing energy out of nowhere, paying for it with the expansion of space. So, as the clock ticked in those first fractions of a second, the universe was not just getting bigger, it was getting more powerful. It was building up a stock of energy that was truly limitless. This energy was the latent energy of the cosmos. It was sleeping energy. It was not manifesting as heat, which, again, is just the jiggling motion of particles, but rather as a tension within the fabric of space-time. This tension created a phenomenon that sounds like science fiction: negative pressure. We are used to pressure that pushes outwards, like air inside a balloon. But gravity is usually an attractive force. It pulls things together. The mass of the Earth pulls on the Moon. The mass of the Sun pulls on the Earth. However, the mathematics of Einstein's relativity tells us that pressure also acts as a source of gravity. And the inflaton field had a unique negative pressure that acted as a form of repulsive gravity. Instead of pulling the universe together, the inflaton field pushed it apart. And because the field didn't get thinner as it expanded, this pushing force didn't get weaker. It stayed constant. A constant push on a fabric that is already stretching leads to a runaway effect. The expansion became exponential. It became faster and faster, doubling in size, then doubling again, at a pace that strips the human mind of its ability to visualize. Let us try to visualize the scale of this stretching. Imagine a subatomic particle, something so small it makes a grain of sand look like a galaxy. Now, imagine that in less time than it takes to blink, that single particle is stretched to the size of our entire solar system. That is the violence of inflation. It took a region of space smaller than a proton and blew it up to be larger than the observable universe we see today. During this process, any stuff that might have existed before, any stray particles, any ripples, any heat, was stretched into oblivion. Imagine drawing a squiggle on a rubber sheet. If you stretch that sheet until it is the size of a continent, the squiggle becomes a straight line so long and so flat that you cannot even tell it was ever curved. The universe was ironed flat. This brings us back to the silence. As space expanded faster than light, it created a horizon around every point. If you were there and you tried to shine a flashlight at a friend standing a few meters away, the space between you and your friend would expand so fast that the light would never reach them. The light beam would try to travel forward at 300,000 kilometers per second, but the space it was traveling through would be lengthening faster than that. The light would be swept backward, like a swimmer trying to swim upstream against a raging waterfall. Every point in the universe became causally disconnected from every other point. It was a universe of absolute solitude. No information could be shared. No heat could flow. This is why the universe was so cold. Heat requires interaction. It requires particles bumping into each other, trading energy, sharing the warmth. But in the grip of inflation, nothing could bump into anything. The dance of particles was stopped before it could begin, frozen by the sheer speed of the stretching floor beneath their feet. But the most important part of this story is not the stretching itself. It is the precarious nature of the energy that drove it. We must return to the metaphor of the ball on the hill. Physicists call the state of the inflaton field a false vacuum. A true vacuum is the bottom of the valley, the state of lowest possible energy, where everything is stable and quiet. That is where our universe sits today. But during inflation, the universe was in a false vacuum. It was stuck on a ledge high up on the energy landscape. It feels contradictory to say the universe was unstable when it looked so smooth and uniform. But stability in physics is about energy. A ball sitting on the edge of a table is technically stationary, but it is not stable. A slight breeze, a tiny tremor, and it will fall. The inflaton field was balanced on a razor's edge. It held a colossal amount of potential energy, the energy equivalent of all the stars and galaxies that would ever exist, compressed into a field that filled all space. This energy was trapped. It was locked inside the field, unable to turn into matter, unable to turn into light. It was just there, maintaining the tension, driving the expansion. It was a dam holding back an ocean of fire. The fascinating question is, why did it stay there? Why didn't the ball roll down immediately? The answer lies in the friction of the early universe. Not friction like sandpaper, but a kind of dynamical friction caused by the expansion itself. The universe was expanding so fast that it slowed down the evolution of the field. It is similar to how a moving object in a thick fluid, like honey, struggles to change its speed. The rapid expansion of space acted like molasses, keeping the inflaton field stuck on its high plateau for just a fraction of a second longer than it naturally wanted to stay. And that fraction of a second made all the difference. It allowed the universe to grow large. It allowed the stage to be built. If the field had decayed instantly, the universe would have collapsed or remained a microscopic curiosity. The stiffness of the field, its resistance to change, bought us the time and space we needed to exist. So here we have the picture of the universe just before the heat arrived. It is a vast, dark, exponentially growing void. It is devoid of matter. It is devoid of light. It is colder than the deepest winter. But every cubic centimeter of this emptiness is vibrating with a pent-up, frantic energy. It is a coil compressed to its breaking point. It is a bow drawn back until the wood groans. The inflaton field pervades everything, a silent ghost governing the shape of reality. It is the architect and the battery of the cosmos. It has smoothed the universe into a perfect, flat sheet. It has blown up the scale of reality from the microscopic to the macroscopic. But the expansion cannot last forever. The laws of quantum mechanics, which govern the very small, ensure that nothing can remain perfectly still on a ledge forever. There are jitters, there are fluctuations. The molasses effect of the expansion is fighting against the natural tendency of the field to decay, to drop to the valley floor. The tension is reaching a critical limit. The expansive force has done its work. The universe is now big enough. It is flat enough. The batteries of the vacuum are fully charged, holding a charge so massive that the human mind cannot quantify it. Nature abhors a gradient. It hates when energy is piled up in one place. It wants to distribute it. The water wants to flow downhill. The heat wants to flow from hot to cold. And the inflaton field, sitting high on its perch of potential energy, is about to succumb to this universal desire for equilibrium. The stretching is about to stop. The silence is about to be broken. The latent energy, which has been used solely to stretch geometry, is about to undergo a phase change. It is about to curdle into reality. We are standing at the threshold of the reheating. The term suggests a return to warmth, but as we have seen, there was no warmth before this. This is the birth of warmth. This is the moment where the potential becomes kinetic. Imagine the sound of a dam beginning to crack. A tiny fissure appears in the concrete. A trickle of water escapes, then another. The structural integrity of the barrier, which held back the weight of 1,000,000 tons of water, is failing. The water is not disappearing. It is changing. It is trading its height for speed. It is trading its potential for chaos. In the next section, we will witness this collapse. We will watch the inflaton field fall from its high plateau. We will see how this smooth, dark energy shatters and decays, dumping its hoard of power into the vacuum. We will see the darkness ignite. This is the mechanism of the fire. This is how a cold, empty universe suddenly became a furnace. The stretching is over. The burning is about to begin. The universe is now a vast, silent cathedral. It has been stretched to proportions that defy logic, smoothed into a flawless, frozen expanse by the relentless push of the inflaton field. We are suspended in that fraction of a second where the cosmos is holding its breath. The ball of the inflaton field is perched on the edge of its high plateau, trembling with the instability of the false vacuum. The energy density is colossal, but it is dark. It is locked away in the geometry of space, unavailable to do the work of creation. And then the stability breaks. The transition from the cold, expansive era of inflation to the hot, fiery Big Bang is not a gentle fade. It is a crash. It is the moment the dam bursts. In physics, we often describe the end of inflation as a decay, a word that perhaps sounds too slow, too organic, like a leaf decomposing on a forest floor. But this decay was the most violent release of power in the history of existence. It was the conversion of the energy of space into the energy of matter. The process begins when the inflaton field finally loses its battle against gravity. The friction that had held it high up on the potential hill, the dynamical friction caused by the sheer speed of expansion, begins to wane. The field starts to roll. It slips off the plateau and plunges down toward the valley floor, the state of true vacuum, the state of minimum energy where it yearns to rest. As it falls, the nature of the universe changes instantly. During the time the field was stuck on the high plateau, its energy was potential and its pressure was negative. This negative pressure was what drove the repulsive gravity, the exponential stretching of space. But as the field rolls down the hill, that potential energy is converted into kinetic energy. The field picks up speed. It rushes toward the bottom of the energy well. Crucially, when it hits the bottom, it does not simply stop. Imagine a marble rolling down the smooth sides of a porcelain bowl. When it reaches the center, it has too much momentum to halt. It shoots past the bottom, rolling up the other side, then stops, reverses, and rolls back down again. It oscillates. It sloshes back and forth, trading height for speed, over and over again. In the early universe, this sloshing was not a movement of matter, but a vibration of the field itself. The value of the inflatoned field began to oscillate wildly around its minimum point. It was like a great, invisible bell that had been struck by the hammer of gravity, ringing out into the silence of the void. This oscillation is the key to the fire. If the inflatoned field had been completely isolated, if it were the only thing in existence, it might have just oscillated forever, slowly fading away as the expansion of the universe dampened its motion, like a pendulum slowly coming to a halt in a resisting fluid. But the inflaton field was not alone. It was woven into a tapestry of other fields: the electromagnetic field, the electron field, the quark fields, all the fundamental fields that make up the standard model of particle physics. During inflation, these other fields were dormant. They were ghosts, possessing zero energy, effectively non-existent. But they were coupled to the inflaton. In quantum field theory, coupling means that one field can talk to another. Energy can flow between them. You can think of it like a tuning fork. If you strike a tuning fork and hold it next to a guitar string, the string will begin to vibrate even though you never touched it. The energy transfers through the air from the fork to the string. As the massive inflatoned field began to oscillate at the bottom of its well, it acted like that tuning fork. It began to shake the other fields awake. It thrashed back and forth with such violence that it disturbed the vacuum of the other fields. This phenomenon is often called parametric resonance. The rhythm of the inflaton's oscillation matched the natural frequencies of the other fields, pumping energy into them with every swing. This was the spark. The energy that had been used to stretch the universe was now being dumped into the production of particles. Suddenly, the empty vacuum was no longer empty. As the inflaton field vibrated, it shed its energy. It decayed into pairs of particles, quarks, gluons, electrons, neutrinos. They erupted out of the nothingness. Remember, in quantum physics, mass and energy are interchangeable. The kinetic energy of the vibrating field was so intense that it could spontaneously congeal into matter. It was a waterfall of creation. The efficiency of this transfer was staggering. In a fraction of a second, the inflaton field dumped nearly all of its energy. It depleted itself. The ball finally came to rest at the bottom of the bowl, its energy spent. The field faded into the background, where it presumably remains to this day, a quiet, spent relic of the dawn. But in its place, it left a universe filled with stuff. The cold, geometric void was gone, replaced instantly by a seething, churning ocean of particles. This is the moment of reheating. It is the moment the universe caught fire. The temperature did not just rise, it skyrocketed. We are talking about a transition from near absolute zero to a temperature of perhaps 10 to the power of 27 degrees Kelvin. It is a number so large it is meaningless to our human senses. It is hotter than the core of a sun, hotter than a supernova, hotter than anything that has existed since. Why was it so hot? Because all the energy that had been stored in the vast, stretched fabric of the universe was suddenly compressed into the motion of these new particles. Heat, at its most basic level, is movement. It is the kinetic energy of atoms and particles bouncing off one another. When the inflaton decayed, it created particles that were moving at nearly the speed of light. They were born running. They were born screaming through the cosmos with tremendous momentum. And because the universe was still relatively compact compared to its future size, these particles were packed together in a density we cannot imagine. They collided with one another instantly. They smashed, scattered, and annihilated each other. This chaos is what we call thermalization. When the particles were first born from the decaying field, they might have been organized in coherent waves like soldiers marching in step. But as soon as they interacted, that coherence was lost. They bounced off each other, randomizing their directions and their speeds. This randomization is the definition of heat. A coherent beam of laser light is not hot in the thermodynamic sense, but if you scatter that light into a chaotic room of bouncing photons, it becomes a furnace. The universe had achieved thermal equilibrium. It was now a fireball. It is important to pause here and reframe our understanding of the Big Bang. In popular culture and even in some textbooks, the Big Bang is described as the initial point of singularity, time zero. But many modern cosmologists view this moment of reheating as the true Big Bang. The singularity, if it existed, was the start of inflation, but the hot, dense, expanding fireball that is described by the Big Bang theory, the one that synthesized the elements and eventually evolved into galaxies, that universe began here. It began when inflation ended. The reheating was the bridge, it was the gateway. It was the mechanism that took a universe of cold geometry and turned it into a universe of hot matter. As the heat took over, the expansion of the universe changed character. During inflation, the expansion was exponential, driven by the constant push of the false vacuum. But once the inflaton decayed, that push disappeared. The engine was turned off. The universe was still expanding, flying apart from the initial kick it had received, but now it was coasting. Gravity began to try to pull it back together. The expansion slowed down, transitioning from the violent, accelerating growth of inflation to the steady, decelerating expansion of the radiation-dominated era. But what a radiation era it was! The universe was now dominated by radiation, particles moving so fast they acted like light. There were no stars, no planets, no atoms. The heat was too intense for protons and neutrons to hold together, let alone form nuclei. It was a soup of fundamental constituents. Imagine being an observer in this new world. The darkness of the inflationary era is gone. You are immersed in a bath of radiation so intense that light is an insufficient word. It is a blinding, crushing omnipresence of energy. Every point in space is glowing with the intensity of 1 billion suns. There are no shadows. There is no transparency. The fog of particles is so dense that light cannot travel more than a tiny fraction of a millimeter before hitting a particle. The silence has been replaced by a roar, not a sound carried by air, for there is no air but a roar of pressure. The plasma is churning. Sound waves, waves of density and pressure, are beginning to ripple through the fluid of the early cosmos. These are the first acoustic notes of the universe's symphony, the vibrations that will one day grow into the large-scale structure of galaxies. This transition from the cold, inflationary vacuum to the hot, primordial plasma solves one of the great riddles of cosmology. Why is the universe so uniform in temperature? We look at the cosmic microwave background radiation today, and we see that it is the same temperature everywhere, to within 1 part in 100,000. If the universe had just started as a hot fire, there is no reason the fire should be exactly the same temperature on the left side of the universe as it is on the right. But because the fire was lit by the decay of the inflaton field, and the inflaton field had been smoothed out by inflation, the fire was lit evenly everywhere at once. It was a synchronized ignition. The dam broke everywhere at the same time. The bells rang in unison across the entire cosmos. The reheating was a global event, creating a plasma that was incredibly homogeneous. The tiny fluctuations, the quantum jitters we spoke of earlier, were preserved as slight variations in the density of this plasma, tiny hot and cold spots that would eventually become the seeds of galaxies. But overall, the heating was smooth, uniform, and absolute. As we move away from the instant of reheating, we leave behind the realm of speculative physics and enter the realm of known particle physics. The energy levels, while extreme, are now within the theoretical understanding of our collider experiments. We know what matter does when it is this hot. It breaks, it dissociates, it reveals its deepest symmetries. The universe has now successfully transferred its capital. It has spent the currency of the vacuum to buy a cosmos of matter. The initial investment of the inflaton field has paid off in a shower of quarks and gluons. The frozen winter of the start of time has given way to the blinding summer of the Big Bang. But this heat is unstable. The universe is still expanding, and expansion is the enemy of heat. Just as inflation cooled the universe down, this new phase of expansion will begin to cool the plasma the moment it is born. The temperature has peaked. We are at the maximum height of the fever. From this point on, the story of the universe is a story of cooling. It is a story of things slowing down, settling out, and finding their forms. The furnace has been lit. The raw materials have been dumped into the cauldron. Now, we must watch what cooks in this primordial soup. We must descend from the heights of reheating into the chaos of the particle era, where the fundamental forces of nature are fighting for dominance, and where matter and antimatter are locked in a war that will decide the fate of all reality. We are now drifting in the wake of the great ignition. The silent, cold machinery of inflation has vanished, replaced by a reality that is screaming with energy. We have crossed the threshold into the era of the primordial fireball. If we could place a sensor in this environment, the readings would be incomprehensible. The temperature is not measured in thousands or even millions of degrees, but in trillions. The density is so profound that the entire contents of the observable universe, every star, every galaxy, every cloud of gas, squeezed into a volume smaller than a single star. It is a realm of absolute chaos, yet it is a chaos governed by rigid, beautiful laws. This is the epoch of the particle soup. To understand this moment, we must discard our understanding of matter as we know it today. When we look around our world, we see solid objects. We see tables, mountains, and oceans. We know these are made of atoms, and we know atoms are made of protons, neutrons, and electrons. But in this first microsecond after the reheating, none of these familiar structures can exist. The heat is simply too intense. Imagine a castle built of wax sitting inside a furnace. The castle cannot hold its shape. It melts instantly into a puddle. In the early universe, protons and neutrons are the castles. They are complex structures made of smaller components called quarks, held together by the strong nuclear force. But the ambient temperature of the cosmos is so high that the binding energy of the strong force is overwhelmed. The moment three quarks try to bond together to form a proton, they are smashed apart by a collision with another high-energy particle. So, the universe is not filled with matter as we know it. It is filled with the raw ingredients of matter. It is a seething, liquid-like plasma of free quarks and gluons. Physicists call this the quark-gluon plasma. It is a state of matter that we have only recently been able to recreate for fractions of a second in our most powerful particle accelerators, but here in the infancy of time, it is the natural state of everything. The soup metaphor is apt, but it perhaps suggests something too thick and sluggish. This medium is electric. It is alive. It is a fluid of light and particles moving at the very limit of cosmic speed. The gluons, the carrier particles of the strong force, are flying between the quarks, trying to glue them together, only to be frustrated by the frantic thermal energy. It is a dance of frantic motion, a cosmic rave where no one can stand still long enough to hold hands. In this soup, the distinction between matter and energy is almost meaningless. We are taught Einstein's famous equation that energy equals mass. In our cold, modern universe, this conversion rarely happens spontaneously. A stone does not suddenly turn into a beam of light, nor does a flashlight beam suddenly turn into a stone. But in the thermal frenzy of the early universe, this conversion is happening everywhere, all the time. Particles are colliding with such violence that their kinetic energy spontaneously transforms into new particles. Two photons of light smash together and create an electron and an anti-electron. Conversely, an electron crashes into an anti-electron and vanishes, turning back into light. The universe is a bubbling cauldron of creation and destruction. Matter is flickering in and out of existence. It is not a stable furniture of the universe yet. It is a transient foam riding the waves of heat. This fluidity extends even to the fundamental forces of nature. Today, we perceive gravity, electromagnetism, and the nuclear forces as distinct entities. Magnetism feels very different from the force that holds an atomic nucleus together. But heat has a way of unifying things. Just as ice, liquid water, and steam are distinct phases of the same substance, the forces of nature are distinct phases of a single, unified superforce. At these tremendous temperatures, the electromagnetic force and the weak nuclear force are fused together into something called the electroweak force. If you were there, you would not be able to tell the difference between a ray of light and a radioactive decay. They were aspects of the same interaction. As we look back even further, toward the very instant of the reheating, it is believed that the strong nuclear force was also merged with them. The universe was essentially perfect in its symmetry. It was a single, elegant equation manifesting as a hot, dense field. But as the universe expands, and it is expanding ferociously every single moment, it cools. And as it cools, that perfection begins to fracture. This fracturing is a dramatic event. Just as water suddenly turns to ice when it hits 0 degrees, the fundamental forces separate when the universe hits certain critical temperatures. These are called phase transitions. When the strong force broke away from the electroweak force, it may have released even more energy, changing the viscosity of the particle soup, altering the rules of the game. But amidst this churning plasma, a desperate war is being waged. It is a silent war, a war of arithmetic, and the outcome will determine whether the universe becomes a graveyard of light or a garden of matter. This is the conflict between matter and antimatter. The laws of physics, as we understand them, are largely symmetrical. For every particle of matter created from energy, there should be a corresponding particle of antimatter. An electron has a partner, the positron. A quark has an antiquark. When energy condenses into mass in this high-temperature furnace, it produces them in equal pairs. And when a particle meets its antiparticle, they annihilate instantly, returning their mass to the form of pure radiation. So, the early universe is a slaughterhouse. Billions of particles of matter are created, only to meet billions of particles of antimatter a nanosecond later. They destroy each other in flashes of gamma rays. If this symmetry were perfect, the story would end here. The universe would expand and cool, the particles would all annihilate, and we would be left with nothing but a bath of cold light. There would be no stars, no planets, and certainly no us. But we are here. The stars are here. This means that something, somewhere in the chaos, broke the symmetry. For every billion particles of antimatter, there were 1,000,000,001 particles of ordinary matter. This tiny imbalance, this deviation of 1 part in 1,000,000,000, is the reason existence is possible. As the cooling continued, the great annihilation took place. The billion pairs destroyed each other, flooding the cosmos with light. But that one solitary survivor, that single extra quark, that lone electron, remained. All the matter we see today, the swirling galaxies, the clouds of nebulae, the hand you are using to hold your device, is made of the leftover scraps of that primordial battle. We are the survivors. We are the tiny fraction that did not vanish into light. The intensity of the radiation we see in the cosmos today is a testament to how violent that war was. There are roughly 1,000,000,000 photons of light in the universe for every single proton. That is the ratio of the annihilation. The light is the echo of the dead. The matter is the residue of the living. As the clock ticks past the first microsecond, the universe is still too hot for the survivors to find safety. The single quarks are still swimming in the plasma. But the expansion is relentless. The volume of the universe is growing, and the energy density is dropping. The temperature is falling from trillions of degrees to mere billions. We are approaching another critical threshold. The glue of the universe, the strong nuclear force, is getting stronger as the energy drops. The strong force has a peculiar property. Unlike gravity or magnetism, which get weaker with distance, the strong force gets stronger as you try to pull quarks apart. It acts like a rubber band. In the extreme heat of the soup, the quarks had so much energy they could snap the rubber bands. They could roam free. But as the heat fades, they lose that kinetic freedom. The rubber bands begin to tighten. The quarks are beginning to feel the pull of their neighbors. They are being dragged together. We are witnessing the transition from the quark era to the hadron era. Hadrons are composite particles, the heavy bricks of matter. They are the protons and the neutrons. Watch as the plasma begins to curdle. 3 quarks, moving slightly slower than before, get caught in each other's strong force field. They snap together, locking into a stable configuration. 2 up quarks and 1 down quark combine to form a proton. 2 down quarks and 1 up quark combine to form a neutron. This is a monumental shift. The liquid nature of the universe is thickening. It is becoming grainy. The free-swimming sea of fundamental charges is coagulating into distinct, heavy nuggets of mass. But this is not a gentle process. The formation of hadrons releases binding energy, keeping the heat high even as the expansion tries to cool it. And these new protons and neutrons are not safe yet. They are incredibly heavy compared to the electrons swirling around them, and they are colliding with each other constantly. The universe is now a few microseconds old. It is roughly the size of our solar system, but containing the mass of the entire cosmos. It is a fog of protons, neutrons, electrons, neutrinos, and photons, all smashing into one another. Neutrinos, those ghostly particles that today can pass through a light year of lead without hitting anything, are at this density trapped. The soup is so thick that even the neutrinos cannot escape. They are part of the thermal bath, bouncing off protons and neutrons, transferring heat, keeping the mixture stirred. The soup is also changing flavor. Neutrons are slightly heavier than protons. In the high-energy environment, it is easy to turn a proton into a neutron and vice versa. They flip back and forth constantly as they are bombarded by other particles. But as the temperature drops further, the extra energy required to be a neutron becomes expensive. Nature, always seeking the lowest energy state, begins to favor the lighter proton. The balance shifts. The number of protons begins to outstrip the number of neutrons. This is a crucial detail for the future of the cosmos. Protons are hydrogen nuclei. They are the fuel of stars. If the universe had remained balanced between protons and neutrons, or if neutrons had dominated, the history of stellar burning would have been radically different. We needed a universe rich in hydrogen to eventually create the long-burning stars that allow for the evolution of life. The cooling of the soup is deciding the chemical composition of the future universe. As we move through the first second of time, the density drops enough that the neutrinos finally break free. They decouple from the matter. They slip through the gaps between the particles and stream off into the void. This is the first release of information, the first transparency of the universe, though it is a transparency only to neutrinos, not to light. These primordial neutrinos are still out there today, a cosmic neutrino background, colder and fainter than the light, ghost riders from the first second of creation. The departure of the neutrinos takes away some of the energy, aiding the cooling process. The soup is thinning out. The frantic collisions are becoming slightly less frequent. The protons and neutrons are now distinct, stable travelers. But they are lonely. They are singular. There are no atoms yet. There are no nuclei heavier than a single proton. A proton is just a hydrogen nucleus, but it is alone. To make helium, to make lithium, to make the elements that will eventually build the complexity of the universe, these protons and neutrons need to stick together. They need to fuse. But the universe is playing a cruel game. It is definitely cool enough for protons to exist, but it is still far too hot for them to fuse. Every time a proton and a neutron manage to find each other and bond to form a nucleus of deuterium, heavy hydrogen, a high-energy photon of light comes smashing in and breaks them apart. This is known as the deuterium bottleneck. The universe is stuck. It is filled with the building blocks of atomic nuclei, but the ambient radiation is too violent to allow construction to begin. It is like trying to build a house of cards in the middle of a hurricane. The cards are there, the floor is there, but the wind keeps knocking them down. We are drifting toward the end of the first few seconds. The universe is now light years across. The temperature has dropped to about 1 billion degrees, The soup has calmed significantly compared to the initial chaos. It is no longer a quark-gluon plasma. It is a plasma of ionized hydrogen and helium nuclei waiting to be born. The chaos is subsiding into a simmer. The grand unification of forces is over. Gravity, electromagnetism, the strong force, and the weak force are now distinct actors playing their separate roles. The antimatter has been vanquished, leaving behind the victor, matter. The quarks have been imprisoned inside protons and neutrons. We are ready for the next great phase change. The hurricane of radiation is about to weaken just enough to allow the house of cards to stand. The era of nucleosynthesis, the forging of the first elements, is about to begin. The universe is transforming from a chaotic soup of raw particles into a nuclear reactor. The heat that was born from the cold vacuum is now being tamed. It is being spread out, diluted by the ever-growing fabric of space. But it is still powerful enough to cook the first elements of the periodic table. The silence of inflation feels like a distant dream. The roar of the particle soup is quieting to a hum. The universe is preparing to manufacture its first solid reality. We are drifting now through the first few minutes of cosmic history. The violent, shattering explosions of the earliest fraction of a second have passed. The universe is no longer a seething ocean of quarks and gluons, nor is it dominated by the strange, exotic physics of the unified forces. It has settled into a state that is somewhat more recognizable to our modern understanding of physics, though it is still terrifyingly hostile. We are entering the era of the cosmic kiln. The universe is expanding rapidly, and as we have learned, expansion brings cooling. The temperature has dropped from the incomprehensible trillions of degrees down to a mere billion degrees Kelvin. To us, a billion degrees is an unimaginable inferno, hotter than the center of any star that exists today. But in the context of the early universe, this is a deep freeze compared to what came before. It is cool enough for the fundamental particles, the protons and neutrons, to survive without being melted back down into quarks. However, there is a tension in the cosmos. It is a tension born of frustration. Floating in this rapidly expanding plasma are the ingredients for matter: protons, which are simply hydrogen nuclei, and neutrons. These two particles are natural partners. They feel the pull of the strong nuclear force, a force that acts like a powerful magnetic snap, yearning to bind them together. When a proton and a neutron successfully click together, they form a nucleus of deuterium, also known as heavy hydrogen. This is the first step on the ladder of complexity. It is the first simple marriage of particles, but for the first few minutes, this marriage is impossible to sustain. The universe is filled not just with matter, but with light. It is flooded with high-energy photons, particles of radiation that are swarming through the plasma like angry bees. Every time a proton and a neutron manage to find one another and bond, a high-energy photon slams into them and shatters the bond instantly. Physicists call this the deuterium bottleneck. It is a cosmic traffic jam. The universe is ready to build heavier elements. It has the raw materials. It has the desire, driven by the strong nuclear force. But the ambient temperature is just slightly too high. The radiation is just slightly too aggressive. The universe is stuck in a cycle of creation and destruction, building millions of deuterium nuclei every second, only to see them blasted apart a microsecond later. It is a race against time. This is because the neutron is a fragile creature. When a neutron is bound safely inside an atomic nucleus, it is stable. It can live forever. But a free neutron, a neutron floating alone in space, is unstable. It has a lifespan of about 15 minutes. If left to its own devices, it will decay, breaking down into a proton, an electron, and a ghost-like neutrino. So, the clock is ticking. The neutrons are dying. With every second that passes, the universe loses more of its supply of neutrons. If the bottleneck does not break soon, if the radiation does not cool down enough to allow the deuterium to survive, all the free neutrons will eventually decay into protons. The universe would be left as a cosmos of pure hydrogen, a sterile, simple place with no complexity, no chemistry, and no possibility of life. We need the neutrons to be saved. We need them to be locked away in the safety of heavier nuclei. And then, gently, the threshold is crossed. The expansion of space stretches the wavelengths of the aggressive photons. They lose just enough energy that they can no longer smash the deuterium apart. The violence subsides. The bottleneck breaks. Suddenly, the dam of nuclear fusion bursts open. It is a moment of profound transformation. Across the entire observable universe, everywhere at once, the protons and neutrons begin to fuse. And this time, they stay fused. The efficiency of this process is startling. It is not like a slow, sputtering fire. It is a flash. Because the universe is dense and hot, collisions are happening constantly. As soon as a deuterium nucleus forms, it is immediately struck by another particle. It grabs another proton to become helium-3 or another neutron to become tritium. And then, these intermediate stages slam together to form the prize of the early universe, helium-4. Helium-4 is a fortress. It consists of 2 protons and 2 neutrons bound together so tightly that it is almost impossible to break. It is the noble nucleus, stable, robust, and energetically favorable. Once the neutrons find their way into a helium nucleus, they are safe. They will not decay. They have found their permanent home. This period is known as Big Bang nucleosynthesis. It is the era where the universe acted as a single, colossal thermonuclear reactor. Imagine the scale of this. When we think of nuclear fusion today, we think of the core of the sun. We imagine a localized sphere of fire surrounded by the cold vacuum of space. But in this epoch, there was no outside. The entire universe was the core of a star. There were no cold spots. Every cubic centimeter of reality was burning with the fury of nuclear creation. But this reactor had a very specific limitation: time. In a modern star, fusion can sustain itself for billions of years because the star is held together by its own gravity. The gravity pushes in, the heat pushes out, and a balance is struck. But the early universe was not stable. It was exploding outward. The density was dropping precipitously. The fusion window was incredibly brief. It lasted only a few minutes. As the universe expanded, the particles were pulled further and further apart. The collisions became less frequent. The nuclear force, which only works over tiny distances, could no longer reach out and grab passing particles. This race between the cooling, which allowed fusion to start, and the expansion, which shut fusion down, determined the chemical composition of our entire cosmos. By the time the reactor shut off, roughly 20 minutes after the start of time, the composition of the universe was set. The Great War of nucleosynthesis was over. The smoke cleared to reveal the victors. The vast majority of the nuclei, about 75% by mass, remained as single protons. They were simple hydrogen. These were the protons that never found a partner, or the ones that resulted from the decay of the lonely neutrons. About 25% of the mass had been converted into helium. This is a staggering amount. 1/4 of all the ordinary matter in the universe was forged in those few frantic minutes. If you look at a balloon filled with helium gas today, you are looking at atoms that were born in this very specific window of time, long before the Earth or the Sun existed. They are ancient relics of the Big Bang, unchanged for 13.8 billion years. There was also a tiny dusting of other elements. A trace amount of deuterium was left over, the ones that didn't manage to finish the journey to helium. A minuscule amount of lithium, element number 3, was managed to be cobbled together, but that was effectively it. Why did it stop there? Why didn't the universe keep going? Why didn't it forge carbon, oxygen, nitrogen, and iron, the elements that make up our bodies and our world? The answer lies in a quirk of nuclear physics and the speed of the expansion. There are no stable atomic nuclei with a mass of 5 or 8. If you try to smash a helium nucleus, mass 4, and a proton, mass 1, together to make a mass of 5, it falls apart instantly. It is extremely unstable. To jump across this gap requires 3 helium nuclei to collide at exactly the same moment to form carbon-12. In the cores of stars, which last for billions of years, this triple collision is rare, but given enough time, it happens. But the early universe did not have billions of years, it had minutes. The density dropped so fast that the probability of 3 particles hitting each other at the exact same instant became 0. The bridge to the heavy elements was out. The universe simply didn't have the time to build the complex structures of life. So, the era of nucleosynthesis came to a quiet end. The great cosmic reactor flickered and died, not because it ran out of fuel, but because the fuel became too spread out to ignite. The silence returned, but it was a different kind of silence. The universe was no longer a frantic soup of transformation. It was a stable mix of hydrogen and helium gas. The ratio was locked in: 3 parts hydrogen, 1 part helium. This ratio is one of the strongest pieces of evidence we have for the Big Bang theory. When astronomers look at the oldest gas clouds in the distant universe, clouds that have never been touched by starlight, they find exactly this ratio. It is a fossil imprint of those first few minutes. But while the nuclear fire was out, the universe was still hot. It was still a blinding, glowing fog. We must be careful not to confuse nuclei with atoms. We have spent this section building the hearts of atoms, the positive cores. But an atom is not complete without its shell of electrons. And in this stage of the universe, the electrons were still running wild. The temperature was still millions of degrees. At these energies, an electron is too energetic to be captured by a nucleus. If a positively charged hydrogen nucleus tried to snag a passing negatively charged electron to form a neutral atom, the ambient heat would instantly knock the electron loose. This state of matter is called a plasma. In a plasma, the electrical charges are free, and this has a profound consequence for light. Light consists of photons, which are electromagnetic waves. Photons interact strongly with charged particles. They bounce off electrons like billiard balls bouncing off bumpers. In the plasma of the early universe, a photon could not travel more than a tiny distance before hitting an electron and being scattered in a new direction. This meant the universe was opaque. It was a fog. If you could have stood in the universe at this time, you would not have been able to see your hand in front of your face. You would have been immersed in a bright, glowing mist. The light was trapped, pinning the matter and the radiation together in a thick, hot fluid. It was a world of white noise, a glowing static. There were no stars to break the monotony, only a ceaseless, bright hum of energy. As the minutes stretched into hours, and the hours into years, the universe continued to drift outward. The drama of the first few seconds was replaced by a long, slow coasting. The excitement of particle creation and nuclear fusion was over. Now, the universe had to wait. It had to wait for the expansion to do its work. It had to wait for the fever to break. The plasma was slowly cooling, dropping from millions of degrees to hundreds of thousands. The orange-white glow of the fog was slowly shifting towards red. This period is often called the photon epoch, because the energy of the universe was dominated by this trapped light. The matter, the hydrogen and helium nuclei, was just along for the ride, buffeted by the intense radiation pressure. The sound waves we mentioned earlier were still ringing through this fluid. The dark matter, which does not interact with light, was beginning to clump together under gravity, but the ordinary matter was trapped in the fog, unable to collapse, unable to form structures. It was a time of suspension. The ingredients for the future were all present: the hydrogen for the oceans, the helium for the stars, the electrons for chemistry. They were all there. But they were kept apart by the heat. They were agitated, unable to settle down and combine into the neutral atoms that form the basis of the visible world. We are drifting towards the final major transition of the early universe. The universe is growing quieter, darker, and colder. It is preparing for the moment when the fog will lift. It is preparing for the moment when the electrons will finally succumb to the electrical attraction of the nuclei, closing the chapter on the primordial fireball and opening the window to the clear, transparent cosmos we see today. The heat, which began as a violent explosion from the vacuum, has now been tamed into a warm, glowing bath. But even this warmth is fleeting. The universe is destined to become cold again. The fire that was lit by inflation is slowly dying, dissipating its energy into the ever-growing void. But before the darkness falls completely, there will be one last flash, one last release of light that will travel for eternity. The recombination is coming. The moment the universe becomes transparent, the moment the first light is set free. We have traveled a colossal distance in time, yet we have only moved a fraction of an inch in the grand timeline of the cosmos. We have witnessed the silent, cold stretching of inflation. We have seen the violent decay of the field that lit the match of the Big Bang. We have watched the universe churn as a soup of quarks, and we have seen it forge the first atomic nuclei in the fires of the primeval reactor. But for all this activity, for all this transformation, the universe has remained a prisoner of its own intensity. For hundreds of thousands of years, the cosmos has been locked in a stalemate. It is a stalemate between matter and light. We are now drifting through a long, monotonous epoch, waiting for the fever of creation to break. The universe is roughly 380,000 years old. In the life of a human, this would be comparable to the first few hours after birth. But in the physics of the early universe, where events once happened in nanoseconds, 380,000 years is an eternity of waiting. The universe is still an expanding sphere of plasma. It is a vast, glowing ocean of gas, primarily hydrogen and helium, but it is not the transparent gas we are familiar with today. It is opaque. It is a fog. If you were to open your eyes in this epoch, you would see nothing but a blinding, uniform glow. There are no stars to puncture the brightness, no galaxies to give it shape. It is a wall of light. The reason for this blindness is the electron. These tiny, negatively charged particles are still roaming free, liberated by the intense heat. They are the gatekeepers of the light. Photons, the particles of light, are electromagnetic creatures. They interact strongly with electrical charges. In this plasma, every time a photon tries to travel in a straight line, it slams into a free electron. It is scattered, bounced, and redirected. Light is trapped in a pinball machine of cosmic proportions. A photon might travel for a mere fraction of a centimeter before being knocked off course. It cannot carry information across the universe because its path is constantly being scrambled. The thermal history of the cosmos is locked inside this fog, unable to escape. The universe is holding its breath, clutching its energy close to its chest. But the expansion is relentless. The relentless stretching of space, the legacy of the initial Big Bang, continues to pull the galaxies to be apart. And as space stretches, the wavelengths of the light are stretched with it. The angry, high-energy gamma rays of the early seconds have been pulled into X-rays and then into ultraviolet light. The energy is diluting. The temperature is dropping. We are approaching a critical temperature, 3,000 degrees Kelvin. This is a specific magical number in the laws of thermodynamics. It is the temperature at which the violence of the heat finally succumbs to the subtle pull of the electromagnetic force. It is the temperature of a transition known as recombination. Imagine the scene. The universe is glowing with a dull orange-red light, similar to the color of a dying ember or a dimmed light bulb. The free electrons are slowing down. For eons, they have been buzzing with too much kinetic energy to be caught. They have zipped past the positively charged protons, ignoring their attractive pull. But now, the cold is catching up with them. They are becoming sluggish. The protons, the hydrogen nuclei, have been waiting for this moment. They cast out their electromagnetic nets. As an exhausted electron drifts past a proton, it feels the tug. It tries to resist. It tries to use its thermal energy to escape, but it is no longer strong enough. It spirals inward. It falls into orbit. With a tiny release of energy, the electron snaps into place around the proton. The positive charge of the proton cancels out the negative charge of the electron. The two charged particles vanish, replaced by a single neutral entity, the hydrogen atom. This is a moment of profound peace. Across the expanse of the universe, in a synchronized wave of chemistry, the plasma is turning into gas. The chaotic, charged fluid is becoming neutral matter. The wild electrons are being tamed, locked away inside the shells of atoms, their days of scattering light over. And this changes everything for the photons. Suddenly, the pinball machine disappears. The neutral hydrogen atoms are electrically balanced. They do not harass the light in the same way the free electrons did. The fog lifts. It is the most dramatic lifting of a curtain in the history of time. One moment, the universe is an opaque wall of glowing plasma. The next, it is crystal clear. The photons, which have been trapped in their frantic dance for nearly 400,000 years, suddenly find the path ahead of them unobstructed. There is nothing to hit. There is nothing to scatter them. They are free. This event is called the last scattering. It is the moment light broke loose. Trillions upon trillions of photons are released at the exact same instant from every point in the cosmos, flying in every direction. They carry with them the imprint of the universe as it was at that final moment of the plasma. They are a snapshot of the infant cosmos, frozen in light. As these photons stream away, the matter they leave behind falls into darkness. The glowing fog is gone. There are no stars yet to light up the dark. The gas is cooling and settling into the deep gravitational wells that will eventually become galaxies. But for now, the universe enters what astronomers call the Dark Ages. It is a time of shadows, of silent gas clouds collapsing in the void. But the light does not die. It travels. This is the echo we have been searching for. The light released at the moment of recombination began its journey as visible orange-red light. It was hot, 3,000 degrees, but it had a long way to go. It has been traveling for 13.8 billion years to reach us. During this epic voyage, the universe continued to expand, and this expansion played a trick on the light. It stretched it. Imagine drawing a wavy line on a rubber band. The waves represent the color of the light. If the waves are tight and close together, the light is blue or energetic. If they are loose and spread out, the light is red or cool. Now, stretch the rubber band. The waves get longer. They flatten out. The light from the Big Bang has been riding on the fabric of space, while space has been expanding by a factor of over 1,000. The orange light was stretched into the red, then into the infrared, the invisible heat radiation we feel from a toaster. But the expansion didn't stop there. It kept stretching. The waves grew longer and longer until they were no longer heat waves, but microwaves. Microwaves are the same kind of energy we use to heat our food or transmit our Wi-Fi signals. They are low-energy, long wavelength forms of light. And today, if we build a telescope capable of seeing microwaves and we point it at the sky, we see the echo. It is everywhere. It does not come from a specific star or a specific galaxy. It comes from the background of the universe itself. If you look at the empty space between the stars, it is not truly black. It is glowing faintly with this ancient light. We call it the cosmic microwave background radiation, or the CMB. It is the oldest light in existence. It is the afterglow of the Big Bang. When we measure the temperature of this light today, it is no longer 3,000 degrees. It has cooled down to just 2.7 degrees above absolute zero. It is a frigid whisper of the inferno that once was, but it is there. It is the tangible proof of our fiery origins. In the mid-20th century, two radio astronomers, Arno Penzias and Robert Wilson, stumbled upon this echo by accident. They were building a sensitive antenna to listen to satellite communications, but they couldn't get rid of a persistent, annoying hiss in their receiver. They thought it was interference from the city or perhaps pigeon droppings on the antenna. They cleaned the machine, they pointed it away from the sun, they waited for night. But the hiss remained. It was constant, day and night, summer and winter. It came with equal intensity from every direction in the sky. They had captured the sound of the universe cooling down. They were listening to the fossilized radiation from the moment of recombination. For those of us old enough to remember analog television sets, we have seen this echo with our own eyes. When you tuned a television to a dead channel between the stations, you would see a chaotic dance of black and white static snow. About 1% of that static was not interference from Earth. It was the cosmic microwave background. It was the frantic energy of the Big Bang, stretched over billions of years, dancing on the screen in your living room. We have been bathed in the heat of creation our entire lives without knowing it. This brings our journey full circle. We began with a question: how did the universe become so hot? We have seen that the heat was not the very beginning. The beginning was a cold, silent expansion, a holding of breath. The heat was the release, the great exhalation of energy when the inflation field collapsed. We saw that heat cook the fundamental particles, forcing them to merge and separate, fighting a war between matter and antimatter, and eventually settling into the stable elements of hydrogen and helium. And finally, we saw that heat set free. We saw it transform from a blinding fog into a transparent wash of radiation that fills the cosmos to this day. The universe we live in now is a cooling remnant. We are living in the aftermath of the fire. The stars that speckle our night sky are essentially secondary furnaces, tiny pockets where the gas has collapsed and reignited the memory of the early universe, fusing atoms once again in the dark. But the true primordial heat is gone, dissipated into the vastness of the expanding void. There is a profound humility in this story. It tells us that everything we are, every atom in our blood, every electron in our nerves, was forged in that brief, intense furnace. We are not separate from the universe. We are the ash of its first explosion. We are the cooled down, clumped together debris of the Big Bang, observing itself. As we look out into the night sky, past the stars and the galaxies, we are looking back in time. We are looking back toward that wall of fire. The cosmic microwave background stands as the ultimate horizon, the limit of our vision. Beyond it lies the opaque plasma, and beyond that, the silent mystery of the inflationary void. The heat has faded, but the story it wrote remains. The universe began in silence. It spoke in fire, and now it whispers in microwaves. It is a whisper that tells us we are here, that we are made of light and matter, and that we are part of a cooling, expanding majesty that has been unfolding for 13.8 billion years. As the cosmos continues to expand, the echo will grow fainter. The waves will stretch further, turning from microwaves into radio waves, becoming harder and harder to detect. Billions of years from now, observers in the universe may no longer be able to see the afterglow of the Big Bang. They may look out into a truly dark sky and wonder where they came from, with no fiery fingerprint to guide them. But we are fortunate. We live in the era of the echo. We live in the time when the universe still remembers its heat. We can close our eyes and feel the warmth of that first morning, knowing that the fire that made us is still there, surrounding us, holding us in the cold, dark embrace of space.